So where we left off was looking at these functions and saying, okay, how do we relate g and x to f without really getting into an analysis of them, on their own? So can we, first of all, visualize what the absolute value of x looks like? We did that. That's that V-shaped graph. And then what happens if we subtract 2 from x before we take the absolute value? And what happens if we just add 2 to the absolute value? What do those graphs look like? And so made a table of values for x, f, and g, and h, and started to plot them. So for f at x, we have the familiar v here. You take 2, and that corresponds to 2. Whoops, there you go, 2. Or you take -3, and that corresponds to 3 on the right side. But when we take those values with g at x, you notice that the function changes, and if I plot my my graph according to the points that I have here on this column, it seems like everything shifts over by 2 units. And indeed, that's what happens when you first either add or subtract a number to x before you perform your function. You get this thing shifting left or right. And you can imagine if you, let's say, have a transparency and an overlay, that you're either moving the graph, or a different perspective of it is that you can move the scale. So maybe the graph stays, and by subtracting 2 from x, you're in fact just relabeling the x-axis as being 2 less than what it shows. Now with h, we get something a little different. We're taking the absolute values, so the function behaves like you would expect, but then we're going to add 2 to the value. So you would expect then that basically just makes the graph where any given value of x goes up by 2. Okay? I'll give you a minute. I see a lot of you still drawing. So we call this kind of thing, when it moves to the side or moves up or down, a translation. Okay, I will move on here. The notes will be posted. In fact, they're already posted if you look at graphing functions. Okay, so transformations. A transformation is not only the translations where they move about, but it's also multiplying and the x, or multiplying the function to make it either expand or contract or stretch or shrink, that kind of stuff.
What was the other one, a translation?
A translation, yeah. And it's not important that you know the fine points between the words. You can call these transformations and be absolutely fine. So if we're going to add something to the function, like this was the case where we had h at x in the last slide, we're just moving the whole thing up or down. We're moving the graph basically c units up when we add c, a constant, to it. Similarly, if we subtract something from it, we're going to shift it downwards c units. And you can see here, it really doesn't change the function in terms of its shape very much. It just either raises it or lowers it. And that's probably the most intuitive shift that we can make, is just adding something to the end. Now, if we add our number to x before we perform the function, we're going to go left and right. And so essentially what we're doing is we're kind of playing with the horizontal scale. Now, you would think if you're going to add something that you would go in the direction of going to the right, where your x-axis increases. But in fact, what you're doing is you're shifting it to the left. Think about what happens to 0. you know, if you have x at 0, f at 0, like the absolute value function, we're going to have that point at 0. But if we're going to add 2 to it, okay, then we no longer have f at 0. We have f at 2. Yeah, f at 2, which would then be 2. So the whole thing has moved to the left. And then if we were to subtract it, we get the whole thing moving to the right. So if we were to take something like that, something that looks like the x squared function, and we were to make a new function where we would move it over to the right 3, and then we would move it up 3, we would have a graph that would look like this, like we've just carried that little parabola up to that point where now it's shifted 3 units to the right and 3 units to the left. And so kind of the key point is the vertex there. That's easy to see, but it also remember that every single point along that parabola shifts to the right 3 and up 2. Okay, so yes.
So even though the right side of a graph is usually positive and the left side is usually negative, it's the opposite?
Well, yeah, and the reason why that happens, you can see it right here, is that if you have, if you're going to add 2 to x, like on this line, if you add 2, you no longer get 2. What you get is the same thing as if you were at 0, where you would get 2. Okay, so this -2, when you're adding 0 to it, it does move it that direction. So it's actually making it act as though it were there. So it is just something to remember. It's not really intuitive like moving up and down. It seems like it's backwards, but in fact, when you really think carefully about what's happening, one of the ways to think about it is that you've actually just take the x-axis and you've moved it to the left a little bit, so you're increasing those numbers. Okay? Okay, so now it's also possible to do what's called a reflection. And a reflection, now we're talking about making the graph similar to what it was before, except that it's going to be reflected at some point off of one of the axes. And this is hard to see with the absolute value function, and it's hard to see with the x squared function. But one of the functions that this really is very obvious is if we take the square root of x. And so let's take a look at several numbers. We have -9, -4, -1, and of course that's outside the domain of that function. So we have no f at x when x equals a negative number. But starting at 0, we take the square root, and I'm going to do 0, 1, 4, and 9. Now, before, what I did when I chose x values, I just chose values like -3, -2, -1, and then 1, 2, and 3. I'm choosing these because they're easy to compute. And so when you're using this point method where you're choosing points, make something that's easy to compute, because it's you'll have a tendency to graph it a little bit more easily. Okay, so let's look at g at x. We're going to take negative x. And so now all of a sudden when we have -9, -9 is +9, so now that works in our function. And you see that the domain here has shifted quite a bit, because now we can put x in as a negative number or 0, but if we put x in as a positive number, we're trying to take the square root of a negative number because we're making it negative. And so here's one that we've changed the domain by changing the sign on here. Now if I put a negative sign out in front of the square root, I get the same values as my f at x, except that they're now negative. And so there that original domain applies, but we have Instead of 2, we have -2. Instead of 3, we have 3. So let me illustrate what this has done. So our original graph of the square root is a curve like this. And so it reflects the fact that you have no values here in the negative, in negative x. You only have values for positive x, and you always get a positive number out of the square root. So really your whole graph looks like this, and you can extend it as far as you want. So on this second one now, if we notice that our domain changes, we're going to not be able to calculate values when x is positive, but calculate values when x is negative. We're going to get a graph that looks like this for g at x. So imagine what this is. We've just kind of, with the x-axis, reflected it. Okay, so if you, for instance, put up a mirror, like if my book here was a mirror, and I have my my graph like this, if I were to put up the mirror like this and look at it, that's what I would see. You know, it would be off to that direction. So it's reflected about the x-axis, like my axis, or excuse me, the y-axis. So my book would be vertical. You know, it would reflect it around the y-axis. Yes?
So how does it work because there's a negative square root?
Well, remember that it's negative x. That doesn't mean that negative x is negative. If we have x is -9, then we have negative 9, which is positive 9.
Right.
Okay? So think about it the way, you know, we were talking about in evaluating functions, or actually I guess it's g at x, is going to be negative whatever I put in here for x. And so if I put in a -9, -9 is perfectly good in the domain. Okay, so now this next one, h, all we've done is we've made these positive values negative once we've applied the square root. So this thing is going to be reflected a little bit differently. Instead of 9 corresponding to 3 up here, so 9 comma 3, we're going to expect 9 comma -3. So it's going to be down here, and our function is going to be below the axis, and so it's reflected about the x-axis. So if we negate x, we're making a reflection about the y-axis. If we negate the function, we're making a reflection about the x-axis. Sorry for my very small handwriting here. I don't know what overcame me, but it got small. Oops, probably went too fast, right? Okay, so I'm going to, while you're finishing those up, I'm going to pass out some graph paper, and I have some exercises for you to try. And so what I'd like you to do when you do this is to first see if you can anticipate what the graph looks like from the original function, and then plot a few points to see if it does work the way you expect it to. And while you're doing this, I'm going to be passing out. You're going to be returning home with quizzes.